Albert Einstein, a name synonymous with genius, revolutionized our understanding of the universe. Born in Germany in 1879, Einstein's theories of relativity, developed in the early 20th century, transformed our perception of space, time, gravity, and the cosmos. Before Einstein, physicists envisioned the universe as a rigid stage where events unfolded against the backdrop of absolute time and space. Einstein shattered this paradigm, revealing a universe where time and space are not absolute but intertwined, forming a dynamic fabric that can bend, warp, and even tear. Einstein's revolutionary ideas, initially met with skepticism, have been confirmed by countless experiments and observations, becoming cornerstones of modern physics. His theories not only explained perplexing phenomena but also opened up tantalizing possibilities, including the potential for time travel. While time travel remains a topic of intense debate and speculation, Einstein's theories provide the framework for understanding its theoretical feasibility. In 1905, Einstein published his theory of special relativity, a groundbreaking work that challenged our intuitive understanding of motion and time. Special relativity rests on two fundamental postulates. First, the laws of physics are the same for all observers in uniform motion, meaning observers moving at a constant speed in a straight line will observe the same physical laws. Second, the speed of light in a vacuum is constant for all observers, regardless of their relative motion. These deceptively simple postulates have profound implications. One of the most startling consequences is that time is not absolute but relative. The rate at which time passes depends on the observer's relative motion. The faster an object moves, the slower time passes for it relative to a stationary observer. Imagine two identical clocks, one at rest and the other moving at a significant fraction of the speed of light. Special relativity predicts that the moving clock will tick slower than the stationary clock from the perspective of the stationary observer. This phenomenon, known as time dilation, has been experimentally verified using atomic clocks flown on high-speed jets. The time difference between the two clocks is minuscule at everyday speeds, but it becomes significant as an object approaches the speed of light. This means that time is not a universal metronome ticking at the same rate for everyone, but rather a personal experience influenced by motion. Time dilation suggests the tantalizing possibility of time travel, at least into the future. If a spaceship could travel at a significant fraction of the speed of light, time would pass slower for the astronauts on board relative to people on Earth. A journey that takes years from the perspective of the astronauts could correspond to decades or even centuries on Earth. Upon their return, the astronauts would have effectively traveled into Earth's future. However, traveling back in time presents a much greater challenge, as it would require exceeding the speed of light, a feat forbidden by Einstein's theories. Section 5. General Relativity, Gravity's Cosmic Dance. In 1915, Einstein published his theory of general relativity, which extended special relativity to include gravity. General relativity describes gravity not as a force, but as a curvature of space-time caused by the presence of mass and energy. Imagine a bowling ball placed on a trampoline. The ball's weight causes the trampoline's surface to sag, creating a curvature. Similarly, massive objects like stars and planets warp the fabric of space-time, influencing the motion of objects around them. This warping of space-time is what we perceive as gravity. Section 6. Warping time and space, black holes and wormholes. General relativity predicts the existence of extreme objects like black holes and wormholes, where the curvature of space-time becomes so intense that it can create shortcuts through the fabric of the universe. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. Wormholes, on the other hand, are hypothetical tunnels connecting distant points in space-time, potentially allowing for faster-than-light travel and even time travel. However, the existence of wormholes remains purely theoretical, and even if they do exist, traversing them would present formidable challenges. Section 7. Time travel paradoxes, a wrinkle in the fabric. The possibility of time travel, while intriguing, raises a host of logical paradoxes that challenge our understanding of causality and the nature of time itself. One of the most famous is the grandfather paradox. Imagine traveling back in time and accidentally killing your grandfather before your parent was born. This action would create a paradox, as your existence would then be impossible. Such paradoxes suggest that time travel, if possible, might be governed by rules that prevent such inconsistencies. Section 8. Science fiction's love affair with time travel. Einstein's theories of relativity have had a profound impact on science fiction, inspiring countless stories and films exploring the possibilities and paradoxes of time travel. From H.G. Wells's groundbreaking novel The Time Machine to the blockbuster film Back to the Future, time travel has captivated audiences for over a century. Science fiction often uses time travel as a narrative device to explore themes of free will, the nature of time, and the consequences of altering the past. While many of these stories take creative liberties with scientific accuracy, they often draw inspiration from the principles of relativity, grounding the fantastical in a framework of scientific plausibility. Section 9. Conclusion. Bridging the gap between science and imagination. Einstein's theories of relativity, born from mathematical equations and abstract thought, have profoundly altered our understanding of the universe. They have opened up a realm of possibilities once thought impossible, including the tantalizing prospect of time travel. While time travel remains a topic of scientific speculation and philosophical debate, its exploration, both in theoretical physics and science fiction, continues to ignite our imaginations. Einstein's legacy lies not only in his revolutionary scientific contributions, but also in his ability to bridge the gap between science and imagination, inspiring generations to ponder the mysteries of the cosmos and the nature of time itself.